Okay, this is the second part to our plate tectonics lesson. Last lecture, we learned about continental drift theory and the hypothesis behind it. And we learned about different evidence of plate tectonics, for example, uh, glaciation and fossils. And now this lecture, we're going to talk about the three different plate boundaries, which are convergent, divergent, and transform. So let's go back and revisit the continental drift theory. So the Earth has an internal structure that is quite varied. We have the inner core, outer core, lower mantle, upper mantle, asthenosphere, lithosphere, and crust. And between the asthenosphere and the lithosphere is called the moho. And tectonic plates float on top of the asthenosphere, and that's where they move. So the lithosphere sits on a relatively plastic layer called the asthenosphere. So if you have a load on the Earth's surface and it pushes downward, the lithosphere can bend. And because the asthenosphere is plasticky, it will flow and move. So an example of this is the continental shelf is a passive margin. And so sediments overlie the lithosphere here. And the lithosphere is relatively rigid and won't move. And the asthenosphere below is soft and it can flow. So this is why not everything is completely flat and it moves, because we have a lot of weight on top of the Earth. That can be with water. It can be with really thick crusts, like huge mountaintops. Okay, so composition of oceanic crust is different from continental crust. And that's the part of the lithosphere that is covered by water versus covered by land. So when we say oceanic crust, we mean that those are the lithospheric plates that exist out in the oceans. Heat flow, the rate at which heat rises from the Earth's interior through the crust is not the same everywhere in the oceans. So more heat rises beneath mid-ocean ridges, and this is where there's small breaks in the plates. Earthquakes are not random, but occur in distinct belts, following trenches, mid-ocean ridges, and fracture zones. So you can see here that this is a map of the tectonic plates, and the little triangles correspond to earthquakes. And we see that there's a high frequency of earthquakes around what we call the Ring of Fire, which is indicated here in blue. And the Ring of Fire goes along the western slope of South America, western part of North America, across Alaska, and over on the eastern side of Australia. That's called the Ring of Fire. So I had mentioned Harry Hess before, and he was the geologist that took up after the founder for plate tectonics. And Harry Hess made an observation that old ocean floor must be consumed somewhere because the sediments on the ocean floor are younger and thinner than the continents. So his concept was basically explaining seafloor spreading, in that parts of the ocean floor are younger and thinner. So where we have places like a divergent zone or this mid-ocean ridge, there's magma rising, creating new plate, basically. And this is relatively thin. And further away, it gets thicker. And in this example here over on the left-hand side, this is an example of a convergent boundary where old ocean floor sinks into the mantle. And we're going to talk about this a little bit more later. Here's some more evidence of seafloor spreading. We talked about paleomagnetics, and so we can look at marine magnetic anomalies. which is the difference between the expected strength of the Earth's main dipole field or the Earth's magnetic field and the actual measured strength at that location. So these anomalies can be attributed to polarity reversals in the Earth's magnetic field. And in deep sea drilling in the 1960s, a series of holes were drilled along the Mid-Atlantic Ridge to look at sediment thickness. And the sediment confirmed that the age of the oldest sediment in contact with the ocean ridge, with the ocean crust gets older the further away it is from the ridge. So we have two ideas here. We have evidence of the magnetic polarity changing within the rock formations, which we talked about quite a bit in the last lecture. And when looking at core samples of these wells that were basically drilled along the Mid-Atlantic Ridge, we saw a difference in thickness as well as a difference in their magnetic field. So here's a here's a figure of the major plates. And depending on how you search for this, some of these major plates can be broken up into smaller pieces, but these are the major plates. And behind them are shaded the continents themselves. So here we are in North America. We're on the North American plate. And specifically where we're located in California, we are up against the North American plate and the Pacific plate. One of the reasons that part of the Northwest gets so many earthquakes is because we have this really small plate there, the Juan de Fuca plate, which is butt up against the North American plate and the Pacific plate. Again, this is the ring of fire that goes around the Pacific plate. But here you can see that some plate boundaries don't intersect continents at all. Again, here's a map of the relationship between plate tectonics and earthquakes. And again, along the ring of fire, you can see that there's many earthquakes that occur. If we go back at the other map, we can see where these plate boundaries are. Let's look at this one here between the Antarctic plate and the Australian Indian plate. That would be down here. You can see that that's where earthquakes occur. So let's talk about why there might be earthquakes at plate boundaries. Okay, first let's talk about the different types of plate boundaries. First is the divergent plate, also known as a spreading boundary. It's where two oceanic plates move apart by the process of seafloor spreading. And as the plates move apart, new oceanic lithosphere forms continually along the divergent boundary. About the hopefully success of this drawing app. And so I'm going to draw a divergent plate. Okay, so a divergent plate is where you have the asthenosphere, and there's the plate boundary located here. And above the asthenosphere is where you have the plate, and this plate is being separated. So this is my lithospheric plate, and the plates are moving away from each other, like so. And in between here at this plate boundary, this is where we get new formation of the oceanic plate. Occur at places like the Mid-Atlantic Ridge in the South Atlantic Ocean. And in this example here, we can see that the lighter blue, shades of blue here, represent shallower waters, and the darker blue are deeper waters. So where we have this spreading zone, from aerial photography, we can actually see that this is thinner here at this plate boundary than it is further away. Okay, so let's talk about oceanic crust at the mid-ocean ridge. As seafloor spreading takes place, hot asthenosphere rises beneath the ridge and begins to melt, and molten rock or magma forms. So magma has a lower density than solid rock, so it behaves buoyantly and rises up through the crust. And so some of the magma cools and solidifies along its path to create a chamber. And so in this example here, we have hot asthenosphere rising through the lithosphere and can cool on its way up to create these chambers, which are made of gabbro, which we will talk about in future lectures when we talk about igneous rocks. And the magma then reaches the surface. And here is where we have our mid-ocean ridge axis, and this is where spreading occurs between the two plates. So this map shows the age of the oceanic crust. Red colors are younger. So we can see here at this plate boundary that we have much younger crust right here. And bluer are older, or I guess cooler colors mean that they're older. So we can see quite a few cool colors here along the eastern side of North America. Cooler colors here just north of Africa and south of Europe. So from this map, it's probably pretty clear to see where those plate boundaries occur. I'm sure that you can kind of trace them here with your eye. I'm going to outline them here as I move along with my mouse. Okay, so lithospheric mantle at mid-ocean ridge. So as ocean lithosphere continues to move away from the ridge axis, it continues to cool. So the lithospheric mantle grows and progressively becomes thicker further away from the mid-ocean ridge. And so there is evidence of this. This is what I mentioned in a previous slide, that if you were to take core, or you were to take measurements close to the mid-ocean ridge, you'd see that the lithosphere is much thinner close to the mid-ocean ridge, and it thickens the further away you are. Okay, so here are the high-level learnings for divergent plate boundaries. Seafloor spreading occurs at divergent boundaries defined by mid-ocean ridges. And this is where new oceanic crust solidifies from the magma that is pulled up through the asthenosphere. And as the plates move away from each other, they cool, and the lithospheric mantle forms and thickens. Okay, so now let's talk about the other type of plate boundary, which is a convergent plate boundary. And this is where we have two plates coming together. So when we have oceanic lithosphere, it is denser than the underlying asthenosphere and can sink through the asthenosphere. So once the end of a convergent plate bends down and dips into the mantle, it continues downward like an anchor falling off the bottom of a lake here. So if you can visualize this, or think about maybe a chain off of a table, like if you have a necklace or something hanging off the table, there's a point at which the weight of it forces itself off the table. And that's what this illustration is trying to show. So over time, that anchor will just continue to pull itself down. So at time one, when we have at a convergent boundary, where say a trench forms, it's starting to slip down. But then at time two, this is where the plate continues to sink down into the asthenosphere. So the downgoing plate grinds along the base of the overriding plate, and this is where we get a lot of earthquakes. And so these earthquakes can occur fairly close to the Earth's surface, but can also happen in the downgoing plate at much greater depths. So the deepest detected earthquake was at 660 kilometers. And this is the transition zone between basically the lower mantle and the upper mantle. So along here at this subduction zone is where we see a lot of earthquakes. So here's a few different examples of convergent plate earthquakes, where we have a convergent boundary between oceanic crust and oceanic crust. This is the 2011 Sendai earthquake near Japan. This was a magnitude 9.1, and the depth of this was 29 kilometers. So if we go back to this other slide and we look at where 29 kilometers would be on this diagram, that is quite shallow. And you may have remembered this in the news. It was quite destructive, and it created a huge tsunami, and that's what was really destructive for the neighboring cities and the coastline. Okay, when we have oceanic crust and continental crust at a convergent plate boundary, in 1964, there was the Great Alaskan Earthquake at magnitude 9.2, and that occurred at a depth of 25 kilometers. And when we have continental plate and continental plate boundary, in 2001, there's an earthquake near India, magnitude 7.7, and this is the depth at 16 kilometers. So these types of earthquakes occur at the different convergent plate boundaries. Okay, so again, a convergent plate boundary where we have a subduction zone is resulting in compression caused by faulting behind the arc. So the overriding plate acts like a bulldozer and scrapes up sediment off the downgoing plate to build an accretionary prism. So if you imagine a bulldozer going along the crust here, and it is building up this accretionary prism here right at the boundary. And here at this subduction zone, one plate is being pushed down into the asthenosphere. Subduction beneath oceanic lithosphere produces an island arc. So out in the ocean, when we have a subduction zone, this creates melting at the point in which the plate interacts with the asthenosphere. And sometimes this can cause extreme amount of heat and pressure, and that can cause plasma to move upwards, and this is where we see volcanic island arcs. So volcanic island arcs occur where we have a subduction of oceanic lithosphere. Okay, so back arc basin exists either where subduction happens to begin offshore. This is where trapping ocean lithosphere behind the arc, or where stretching of the lithosphere behind the arc leads to the formation of small spreading ridges behind the arc. So here in this diagram, we can see here's our subduction plate here. We're creating a small trench, and this is where that bulldozer is creating that accretionary zone right here. We have melting with the plate at the asthenosphere, which creates our volcanic island arc. And in this example, we also have a divergent boundary where we have melting of the asthenosphere coming up through this ridge. Okay, so I'm going to draw a convergent boundary. So at a convergent boundary, we have plates that are coming together. So we could have a plate that is subducting into the asthenosphere. So these are the plates. Then this would represent the asthenosphere in here. And we have, this is where two plates are coming together. So that's when we have a subduction zone. But we could also have an example where the two plates are coming together and they kind of butt up against each other. And this is where we see the formation of mountains. Those are supposed to be mountains. I know you're impressed. Again, this is where we have two plates that are coming together at a convergent boundary. That we're going to talk about is a transform plate boundary. At transform boundaries, one plate slips past the other along a vertical fault. And the slip occurs along the segment of the fracture zone between the two ridge segments. So here's our fracture zone. And don't worry too much about the labeling of A and B here. What really you need to notice here is that they're spreading relative to each other. So one plate, if this is the younger plate, one is moving, this is moving in this direction, and the arrow indicates that this plate is moving closer towards us. So here's an example of a transform plate boundary. Again, this is where one plate slides past another, but no new plate is formed and no old plate is consumed. So new plate is formed at divergent boundaries. Old plate is consumed at convergent boundaries. So neither of those occur with a transform plate boundary. So not all transform faults occur in oceanic lithosphere like the San Andreas, which is what we see here. We're actually pretty close to the San Andreas fault, which is the plate boundary between the North American plate over, which is on the east side of the San Andreas, and then on the west side is the Pacific plate. And we're located pretty close. In fact, you've probably driven over the San Andreas plate, or I'm sorry, the San Andreas fault, and have crossed the plate boundary yourself. So here at the plate boundary, the Pacific plate is moving to the north, and the North American plate is moving to the south. So I'm going to pause and draw this for you. About it in 3D, so I'm going to try and draw this in 3D. So if we have one cube here, and let's say that this cube is moving in this direction towards us, and we have the other plate that is moving further away from us. So this one is going this direction. And this is where we have the slipping occur right between these two plates, right along here. And the only way that you can actually see this is through the surface expression. So we see the surface expression between these two plates, and that's the only way to really see the vertical faulting. It's not like we can see this very easily, like you would a new plate rising between the plate boundaries, for example. So this is an example of a transform plate boundary. From boundaries, one plate slips past the other along a vertical fault. And there's no production or destruction of lithosphere at a transform boundary. And most transform boundaries link segments of mid-ocean ridges, but some, like the San Andreas fault, cut across the continental crust. So here's a video about the formation of, or I guess it's about the transform plate here, and how the San Andreas fault is formed and how the coastline has gotten its shape, and where the Baja of California used to be is quite different than where it is today.
Earthquakes are common in the Gulf of California, continuing in a fairly linear trend southeastward from the state of California. Stepping back, we see that these earthquakes define the southwestern margin of the North American plate between California and Middle America. Here, we'll focus on the Gulf of California rift zone, a divergent margin which is propagating into California. It is a transitional corridor that connects the East Pacific Rise spreading ridge to the south with the San Andreas Fault Zone in California. Extension and strike-slip faulting are causing Baja California to separate away from mainland Mexico, thereby opening the Gulf of California as though it were being unzipped. In reality, the waters of the Gulf of California hide connecting stair-stepping seafloor spreading ridges with right lateral strike-slip motion on classic transform faults. This collection of faults and ridges forms a continental rift system that is tearing the Pacific Plate apart from the North American Plate. If we zoom in, we can see the processes occurring. As the lithospheric plates move apart, heat rises beneath the mid-ocean ridge. Magma forms at shallow pressures and creates new rock at the spreading ridges. The plates move away in conveyor belt-like fashion. Movement between the ridges is accommodated by transform faults where large earthquakes occur due to friction between the plates. Smaller earthquakes also occur along the ridges. Backing out to map view, we see the simplified San Andreas fault system cutting through California. As the movement of the plates continues along this plate boundary, it is forcing Baja California away from Mexico and causing Santa Barbara and San Diego to migrate northward towards San Francisco. Zooming into this smaller region for a more detailed look, we will go back 20 million years to watch how the Gulf and coastal areas developed. This animation by Tanya Atwater shows a tectonic model for the 20 million year evolution of the region, depicting the rotation of the transverse range blocks, the breakup of the continental shelf, as well as the opening of the Gulf of California as the Pacific Plate grinds northward against the North American Plate. The Baja California Peninsula and most of southwestern California is a remnant of the North American continent that was sheared off and moved to its present position. Earthquakes in the Gulf are more of a nuisance than a threat. However, the on-land part of this spreading ridge extends into Baja California, Mexico, and the Imperial Valley of California, where it is transitioning from ridge transform boundary to the continental boundary. This area is especially vulnerable because it is underlain by soft sediment that can shake violently during earthquakes. Scientifically, the Gulf is a classic place to study the early stages of the opening of an ocean basin.
So what I like about this video is that it explains pretty well about the formation of basically the Baja California and how our local geology here in Southern California is so impacted by the plate boundary, the transform plate boundary of the San Andreas. And this video also mentioned that we get so many earthquakes along the San Andreas because of all that friction that occurs between plate boundaries. So this is something that I may not have discussed thoroughly enough already, is that earthquakes occur at these plate boundaries because there's so much force being acted on at these major intersections around the globe. And this is really where there's a lot of stress going on, and this is where we get earthquakes because of the amount of stress and force, and therefore friction that occurs. So throughout this semester, we're going to talk a lot about Southern California geology because it's local, and we have so many great examples to use throughout the semester to explain geologic concepts. So we're going to be talking quite a bit more about the San Andreas. Okay, so there's a few special locations that occur around the globe for plate boundaries, and the first is called a triple junction. And this is where 3 plate boundaries intersect. For example, this intersection occurs between the Indian plate, the African plate, and the Antarctic plate. So the ridge intersects 2 arms of the Indian Ocean Ridge here. Another special location is hotspot. And this is where volcanoes of both volcanic arcs and mid-ocean ridges are plate boundary volcanoes. Like this is where they're formed due to plate boundaries specifically. Remember, volcanic arcs are where we have subduction and then the friction there occurring with the asthenosphere. This is where we get those volcanic arcs. But not all volcanoes are plate boundary specific. So hotspots occur at the end of a chain of extinct volcanoes. So an example of hotspots is Hawaii. And this is where we have a mantle plume, which is like a column of hot rock that rises up through the mantle, the base of the lithosphere, and rises up through. It breaks through a weak spot in the lithosphere, and it creates a hotspot for these volcanoes to form. And because the plate, in this example with Hawaii, because the Pacific plate is moving in a north-northwesterly direction, this is where we get a chain of volcanoes. And when we say a chain of extinct volcanoes, meaning that further away islands like Kauai and Oahu, they're no longer volcanically active, but they once were. But because the plate has been moved along this hotspot, this is where we get the chain of islands. And now the island of Hawaii is volcanically active. Okay, so here's a summary of those special locations. So first is a triple junction, and that marks the point where there's 3 plate boundaries joining. A hotspot is a point where volcanism occurs independent of plate boundary movement. And hotspots may be due to melting at the top of a mantle plume. And so again, as the plate moves over the plume, a hotspot track develops. Okay, so plate boundaries form and die. I've mentioned this already, but let's go over it again. So oceanic plates form and are later consumed, while continents merge and later split apart. So this is a whole cycle with plates around the globe. And rifting is where new divergent boundaries form when a continent splits and separates into 2 continents. So you might see this if you remember back to the video about how different the Earth looked when we called Pangea, that large mass. And this is where you could have a plate boundary that actually separates the 2 continents. And a collision is where we have a convergent boundary ceases to exist when the buoyant crust, such as an island arc, moves into the subduction zone and in effect jams up the system. And this is where we get large mountains. So these are the 2 places where boundaries merge and drift apart. They're called rifting and collision. So how do the plates move? Well, they move through convection. And this is where we get plate motion. And convection is where we have upwelling, is when we have the hotter asthenosphere rising, and then downwelling is when shallow and colder asthenosphere is sinking. Again, so think about this as like a lava lamp, if you've ever played with a lava lamp. So you have hotter asthenosphere that rises, and then as it cools, it sinks back down. So this convection that's occurring in the asthenosphere around the Earth is what creates plates, or it's what causes the plates to move. And so we have some modern studies that show how convection is flowing and how complicated these flow patterns are. It's not uniform. And so this kind of looks like a brain here. This is mantle convection simulation. So you can see that the colors represent temperature. And I'm guessing that this is on a 0 to 1 scale. So, red is likely very high temperatures, and blue are cooler temperatures. So we see that as the asthenosphere is getting warmer, it rises up closer to the crust. And then further away from the zone, it cools and then sinks back down. So it creates this cycle, and this is called convection. So let's watch a video about how they model convection and where the science is going to explain convection.
Geology is very much concerned with the history of the Earth. Why does the Earth look today the way it does? And if I take plate tectonics as the example, the current positions of the continents, the current positions of the plates are a reflection of the motions that have happened on the surface of the Earth over time. But we've learned that that expression on the surface is really just a reflection of much larger processes in the interior of the Earth. Convection is a process that moves heat around. Hot material comes up, cool material goes down, and in the interior of the Earth, convection occurs throughout the Earth's outer core and mantle. The mantle is made out of rocks. Under the very high temperatures and pressures of the interior of the Earth, rocks flow. So when we think about rocks as something that cannot move, on short time scales, that is correct. But on the geological time scales of millions of years, rocks slowly flow. And that is what allows the convection to occur. Yeah, and maybe even a little bit more already rotated. Over the last 20 years, the visualization of computer models representing fundamental principles of physics have allowed us to understand the convection processes inside of the Earth much better than we used to know. When the colors are yellow, they are hot rocks, they're rising. All these red regions here are rocks that are unusually dense and cool. We have also learned a new way of using the computing model by combining these fundamental principles of physics with observations delivered by geology.
What I was finding interesting was this structure here below Africa.
Oh, yeah. Africa is known from geological observations of many kinds to be an area that has risen over time. The mechanisms for this rising have always been hotly debated. The ability to connect these observations of Africa as a continent that rises to the convection processes beneath the plate and the rising of a plume inside of the mantle has allowed us to think about the convection process not just as a fundamental process that must occur, but as a process that we can link to specific regions and improve our understanding of the surface of the Earth today.
Video talked more about convection and how convection plays a huge part in how plates are moving. And it also shows that it's not uniform throughout the asthenosphere. And so therefore, plate velocity is not the same around the globe. So motion takes place at rates between 1 to 15 centimeters per year. So let's think about what 1 centimeter looks like and about what 15 centimeters look like, and think about how much the Earth is changing in 1 year. So when we think about large changes over millions of years, like that video I showed you last lecture about how the plates have moved significantly in the last 100 million years and will continue to change significantly in the coming millions of years, we can look at how we can see how plates have actually moved in even our own observable time. So how do we measure velocities today? Well, we have now really accurate satellites and GPS systems that can measure plate movement. So this map here is really interesting because it shows the arrow direction of the plate, and the length of the arrow, or the length of the vector, shows the longer it is, meaning the faster it is. So you can see how quickly the North American plate is moving slightly westerly. You can see the Eurasian plate moving north relative a little bit slower. You can see that these arrows here are a little bit shorter. And these are where the plate boundaries occur. So you can see the arrows over the plate boundaries here show that these plates are moving away from each other. So this is a divergent plate boundary. Okay, so plate motion summary. So plate motion takes place because plates are acted on by the ridges pushing, pulling against each other, as well as convection. So the motion takes place at 1 to 15 centimeters per year. And the relative motion specifies the rate that a plate moves relative to its neighbor. And so we can measure this through GPS. And now we can detect relative plate motions more directly and more accurately. Okay, so the things that we've covered in the last two lectures are continental drift theory, talked about the evidence of plate tectonics. And then in this lecture specifically, we talked about the three different types of plate boundaries: convergent, divergent, and transform. And it's not listed here, but we also talked about a few special cases like triple junction and hotspots.